curso é filmado. Eu entendo por essa razão muita gente quer acompanhar pelo YouTube. Mas como eu já tenho um curso filmado em português muitos anos atrás, então se você procurar no site do IMPA no YouTube, você pode ver aulas em português. E eu vou dar essa vez em inglês. Tá? Então, só para ter uma versão gravada em inglês também. A ideia é que o curso eu vou dar aulas, vocês vão ter exercícios que vocês entregam, e no final vai ter prova que minha expectativa é que até carnaval eu acabo com aulas, então durante carnaval vocês têm tempo para preparar e na semana depois de carnaval vamos ter prova. Okay, então, so I'll speak English, no, from now on, and I hope this is fine. Okay, so eu tenho que ficar com esse formato. So our course has three. Well, first of all, you can always send me email if you like, if you have any questions. So it's Alexei impa.br. I will also be putting the material on a web page, so it's just same thing. And then you go to the teaching section, and then there will be material related to this course. It's not there yet, but I will put. So I'll be putting here. So what I have the notes, typed notes for almost all of the course, and also I will be putting the exercises there. So the course consists of three essential parts. So in the beginning, I will recall you the classical mechanics. Classical mechanics. From trying to be more abstract, so giving some. Essentially, I'll try to give classical mechanics from point of view, not just how it works, but why. Why it has the form as it has. So this probably will take 5-6 lectures. Then we will have a large part oscillations. And finally waves. So I have so you will find here that there is there are type no PDF with the notes for the classical mechanics for the second half of the oscillations. I don't have first half, unfortunately, except that I have these the written notes, and then I have also the PDF for the part of the waves. So this you can see in PDFs. Okay, good. So that's a plan. Well, organization, organization. So we have a class for 2 hours. 2 hours is a bit too long for me, so we split it into 2 pieces. So we have coffee in the middle. Okay, so take 1 hour, coffee, 1 hour, and just asking questions, please, whenever you want. So we start. So I will be giving the part of the classical mechanics. Of course, we have just few lectures on classical mechanics. I can give you much. I will try just to give you essential principles that we will use later in other parts. So we will start with Hamilton's principle. So this also often called principle of least action. So in order to define the principle, first of all, let's you can see? Okay. So let's first define where the system is. So first we say that we consider the physical system in a space. So we have a space. So it's given by points with 3 coordinates, which is a points in 3-dimensional. So we have 3-dimensional space and we have time. Which is real. Okay, and then the system that we will consider, they are system of material points. So it's material point, or you can say it's point particle or it's point mass. So there are different definitions or different words for this. So material point is a small object. Defined by its position at time, at given time, no, at any time t. So material point is the object for which we only need coordinates. So it's usually how physicists formulate it, that it's small enough so that only its position, its 3 coordinates matter and nothing else is important. So material point is, to define material point, we just have to define which position in space it takes at every time. Okay, and our system, our physical system that we will consider is a system of points. So system of material points. So we will index them by letters. So it will be XA, XB, XC, and so on. So all of them points in 3-dimensional space. And then, so what it is, means that we have a space with 3 coordinates. And then we have a point A, point B, point C. So, and so some number of points, and then we can just put these vectors together to give it just single vector, which defines the whole system at once. So state of the system. The state of the system is given by the vector Q, which is where we just put all these vectors together in a single vector. So what it is? So every x, so every xa is x1a, x2a, x3a, and the same for b and c. So these 3 coordinates. So we can put just all of them one after another. x1a, x1b, x1 2a, 3a, then will be x1b, x2b, and so on. There will be such a long vectors which just list all coordinates of all points. So this vector in some n-dimensional space, and n is of course 3 times number of coordinates, number of points. So whenever you have this vector, which can be long if you have many points, you define what is your system. And finally, the evolution is given by the function. So you have to define Q as a function of time. So whenever you have this function as a full vector as a function of time, you know at every time where the whole points are. and the change of their position with time is exactly what we call evolution. So that's a simple concept. In principle, what that means that instead of collection of points in three-dimensional space, you go to the n-dimensional space. And then represent the full system by the vector, by 1 point. So collection of points means 1 point in n-dimensional space, and the motion of a system where each particle moves, it's just single trajectory here. So this we will call trajectory of physical trajectory. It's kind of clear, no? I hope. Okay, so we need to define. So the question is how to define Q of t. So what are the what you should assume in order to have some mathematical apparatus which or equations of motion, no, finally, which define the trajectory. So this is our goal. So our goal is to find this function, no? Because evolution means finding this function. So how we do this? So this is here the Hamilton principle comes. So it suggests. So Hamilton principle suggests, let's first formulate it in non-rigorous way, just as an idea. So it suggests that dynamics can be determined as a minimum in more general extremum, but we will talk only about minimum of some functional depending on the trajectory. So what it means? It means that for every trajectory, functional means that for every trajectory we give a number. So Hamilton principle just tells that you can there is a function which gives a number to every trajectory, and the right trajectory is the one which gives a minimum of that function. So that's not really big of a constraint, right? So in principle, it's natural that if you have certain, you can always create a function which gives you minimum whatever you want. So the Hamilton principle suggests that this approach can be taken here. So specifically, we consider the function, the trajectory as a function. So in the fixed interval. So we fix interval between two times. And what this function is. So this functional is called action. So action is some function S which, given this trajectory, so whenever you have the trajectory on this interval, it assigns a certain number. So there is a law which you give me trajectory, it gives you a number. So the Hamilton principle, it tells that S should attain minimum on a physical or true trajectory. So that's mathematical formulation. So the next question, what is S? What is S? So the third question for choosing the first step for choosing S is to first of all here there is a restriction, right? So there is a restriction. It tells you that whenever we use this action and it gives a number to the piece of the trajectory, so we have a like trajectory vector q as function of time. We have the interval of time where we consider it. So that's vector, so we have a trajectory. And it tells you that among all the other trajectories that you can choose, this one will give a minimum, this one will define a minimum of the action, right? So the first restriction which is given by this formulation is that the dynamics at each interval does not depend on what was before and what is after. So this is important. But then there is another principle, is that this same principle should work for every interval. So for example, if you put t0, t1 here, then you can also divide this interval into two pieces, with t2 in the middle. And then the principle should be applied equally here and there, right? With the same, apparently with the same type of function S. And then you can even cut it into more pieces. And then it should be working at each subinterval with the same S. And then if you think a little bit, then there is a convenient form, a general form of the function which satisfies this property for every splitting of the interval. And this is integral. So you already see that this looks like splitting into pieces, looks like integration, right? So you split into the pieces. So the way which satisfy this property that it will be the same functional S for every interval is just taking the integral, right? It's taking the integral. It means that if piece of time, and what defines the function of small piece of time is value of the function and derivatives, right? Because value and derivatives define function with any approximation in a small interval. So the important assumption is that it depends on time, depends on coordinates, depends on velocities, and that's it. So this is really the strongest hypothesis in the whole theory. Because what we say is that this function does not depend on higher derivatives. So whenever you want to find a functional which is minimized, it should be represented as an integral of some function, because it should be invariant with respect to splitting of interval to the partition of the intervals. But what we assume is that within each small interval, it only depends on coordinates and velocities. So what you can say here is, in principle, one may take the function L with any number of derivatives, right? For example, until some derivative k. So why we take only the first? So first of all, if you take less, it will not work. So you will see that, you can see that if you take just function L, which does not depend on derivative, you will not have any theory coming out of the least action principle. So after we do the analysis, you can repeat the analysis and see that actually the just taking dependence on coordinates and time does not give any theory. Does not give any theory which is have any good sense for describing the nature. So why we don't put a higher order derivative? This is already a question. Well, you can have different. It's more like philosophical questions. So one is because this is the simplest version which works. Second, of course, is because the theory which comes out from this formulation agrees very well with the nature. So this works. The third is that you can write the theory with higher number of derivatives, and you will find some. In principle, it works, but there will be problems which do not appear in this formulation. So there are many reasons which kind of suggest that there should be only the first derivatives here, but there is no really any reason which proves that it should be so. So actually, the only way how you, I think, in more rigorous sense justify this form is by deriving this theory from more advanced physical theories, which is go beyond the classical mechanics. So this is what we just take for granted. So we take this form and that's it. But there are interesting things about it, discussing this issue of why we only have time derivatives. Okay, so now we can formulate the Hamilton principle in full. So it tells that the action which is this, attains a minimum on a physical trajectory so physical trajectory, whatever other trajectory you put on this interval, S should be bigger or equal. But now there is extra condition again. So a minimum among what? So there is a physical trajectory and there are other trajectories. So from what set of trajectories you consider this minimum? So this will be among all trajectories with the same endpoints. So endpoints were fixed. And this is really strong limitation, which is rather counterintuitive, because why you start someplace and you want to find a trajectory, and in order to find a trajectory from Hamilton principle, you should know the first point and the last point. So kind of not very nice condition. But what we will see from the derivation now is that nothing of this will work without this condition, just this. So you kind of, the mathematics just force a kind of condition like this to be present. If it's not present, it doesn't work. So from that point of view, we either assume it or we just don't have a theory. So essentially, what do we say is that, again, if you put time and put coordinates, so we have initial time, we have final time, and we fix first initial point, we fix the final point, and our trajectory is the one which gives the minimum among all trajectories which have the same ends. So you can compare this integral for all different trajectories which have the same end, and the right one will give a minimum. So that's quite abstract so far, no? So now, but we do not, so far we don't assume much about the system. We just assume some general abstract relations. So we assume that, so what we did is we assume that there is a function which gives the minimum. Then it's natural to represent the function as an integral from natural properties. We have and we have two strong limitations. One is that we only put first derivative in this function L. So this function L is called Lagrangian function. Or often just say Lagrangian. And then we say that this integral should take minimum on physical trajectory. And under this extra condition, but this extra condition is also naturally imposed. So far, many things are rather natural. So we don't give really strong limitations up to now. So now we can start becoming more concrete. And there are two questions that we will have to answer. So first, what this minimum principle gives us, how especially it describes the dynamics. And the second is whenever we know what this principle gives as an equation of motion, the next question will ask, what is L? So for which considerations we define the Lagrangian function. So we start with the first and then continue with the second. So first is equations of motion. So we have to derive equations of motion. Okay, so let's start. So let's start with just n equal 1. So our vector q is just a number. So it's like think that you have one particle on a line, right? So it's just q is one number. From general perspective, it doesn't matter because our formulation is general. So what we want to have is we want to have the action, which is integral where now q and q dot. So okay, so what? Given endpoints. So the Hamiltonian principle tells us we give you 2 points, we give you function L, so find the trajectory which takes the minimum. So how you do this? Consider a small perturbation. So we consider the trajectory which is perturbed with some other function. So epsilon small, and any function h of t, where h at t0, h t1 is 0. Well, of course, we're dealing here with functions which are well behaved. So it's continuous, smooth, whatever good function. So it's never discontinuous function. So we take a perturbation. And the Hamilton principle tells you that if you compute this action for this function, for the perturbed one, and compare it with the action which is computed for the physical, so the physical takes the minimum. So this should be less or equal. Less or equal for any epsilon and h of t of this kind, right? So this is a condition of the minimum, less or equal. So now we can analyze this condition by considering this left part as a Taylor series. So take Taylor series. Well, you already see, I didn't tell from the beginning what are the preliminaries of this course. So generally, I expect that you know the basics of calculus and some basics of linear algebra. You see, it's not simple all the time, but I think with the basics you can understand, or at least you can understand what you need to learn extra if you need to understand. So I don't really expect very deep knowledge of the analysis for all of the course. Okay, so we take the Taylor series. So how we do it? So this q plus epsilon h is by definition is this integral. So what it is? L t q plus epsilon h. Let's put it exact. No, q plus epsilon h q dot plus epsilon h dot dt. And we expand it in the, so this is a function, so we consider this function as a function of epsilon, and you can expand it in a Taylor series in epsilon. So Taylor in epsilon. So what it is, the first term is you just put epsilon to be 0. So this is epsilon 0. And then plus epsilon multiplied by the derivative of this function at epsilon 0. And derivative is epsilon is here and epsilon is there. So derivative takes the form dl dq. And so it's a chain rule, right? So you take derivative of L with respect to this component and this component with respect to epsilon. And then the derivative of L with respect to this component, and then this component with respect to epsilon. So it will be dl dq dot h dot dt. We don't need the parentheses. And then higher order terms, which we actually don't need. So this is derivative, right? Good. Okay, so put it inside. Put it there. So what do we have? So we have, on the left-hand side, we have this integral. And it should be big or equal to this other integral. So the first terms, they obviously cancel. So you put 0 here. And then when you put 0, you can also cancel epsilon, right? Because epsilon is non-zero. 0 epsilon is not of interest. So it means that at the end, we have T0, T1. Bigger or equal than 0. So this is for any, again, for any epsilon and h of t. Okay, the next step is we need to deal with this second term. So we take it dl dq dot h dot. Let's write h dot as in full. So what you can remember from calculus is this is a function by the derivative of function dt, so you can integrate it by parts. So you put this derivative to the left. Integration by parts. So integration by parts with this function nh. So dl dq dot h between the limits, and minus the integral, and where you put the derivative on the other side. And here is where we use these conditions that points are fixed. Since points are fixed, remember that the perturbation is 0 at both sides, and this kills the first term. So this is 0 because this kills the first term. And this term is if you don't kill this term, it's problematic because you see, because we need to have it. We need to have this condition to be satisfied for any h, right? It should be bigger than 0 for any h. And if this term is not 0, you see you have the one term which is dominated by h in the interval, and another term which is dominated by h at the ends. So if this term is not 0, then by choosing different h, you can make you can fully control the value of the integral by the first term. And this will just break the whole theory. So you can check that. Essentially what you can check is that the theory will only work if L does not, if this is 0, and if it's 0, that means that L does not depend on derivative. And then we come to the theory where Lagrangian does not have derivatives at all. And I already mentioned this does not give any physical meaning. So we have so this is where this condition comes out, that points should be fixed, because if we don't fix the endpoints, we don't just this doesn't bring you anywhere. Okay. So this is 0. So at the end we have just this part. So then let's put this expression back into the inequality. So what we have is that integral between t0 t1 dl dq, and now h can be put outside of the parentheses dt. No. So now what do we have? So it should be true for any epsilon and h. So now epsilon does not enter the first term, and epsilon only enters in the second term. So smaller epsilon, smaller this term is. So what we need to control is the first term. And the first term should be positive or 0 for arbitrary h. But h can be positive or negative. So if it's positive, then minus h will give a negative value. So it means that the only way how this can be true for any epsilon is in h if this term is 0. Yeah, so that means that this term is 0. And this gives us equation of motion. So we just, since it's 0, we can multiply by minus 1. And we get what's called Euler-Lagrange equation. So you see, we did quite a successful step. We started with the principle which just tells you something should attain minimum, and we ended up with equation, which is already something concrete. Okay. Probably have to give a short observation of our notations. So you see what these notations sometimes are confusing from the first sight, because we use partial derivative and we use d dt. So usually what we say is that we separate the meaning of the partial derivative. For example, of the function of the Lagrangian function, right? So it's dl dt, dl dq, dl dq dot. So it's a derivative with respect to each coordinate. So this is what's called partial derivative. So it means that you consider this function as derivative of t with fixed qq dot, and just take the first derivative. Or here you consider the function with a fixed tq dot, and consider differentiate with the second, and here we differentiate with the third. So this is a standard definition of partial derivative, and we also have a what's usually called material derivative. Or it's a derivative along the trajectory. And this is which we define d dt with a straight d. Derivative of time where all coordinates are considered as a function of time. So you have the meaning of this d dt is that it's you use the chain rule, right? So t enters here, enters there. So first term will be partial derivative, then will be derivative with respect to q and dq dt, which is q dot. And then you have derivative with respect to the second, third. And derivative of the q dot with respect to time will give you q double dot. So this is the meaning of this expression. So this expression means that here we take partial derivative, here we take partial derivative, but this is a full derivative. Well, essentially we arrived to our goal. So what is we arrived to our goal, but for n equal 1. So just for n equal 1, but of course n equal 1 is an interesting case, but we have general n. So what equation of motion you get for arbitrary n, which means the arbitrary number of particles. So for any n, so bigger or equal than 1. So what you take? So what you do? You consider, you fix some coordinates between 1 and n. So you fix some coordinate and then take and perturb in the same way you perturb, but you perturb just this coordinate. With other components qg not equal to 1, not to I, fixed. So you perturb, now q is a vector, right? But you can perturb just one of the components. You perturb one of the components and just do keep the other components fixed, and you can just do the whole analysis in the same way. So there, I can keep it here as an exercise. So you can do the whole analysis in the same way, which will essentially will not change because other components just are kept fixed. And you get the same equation of motion, but for every I. So what you you obtain it for every I. You have just the same equation of motion as we did, but with respect to every component. And in this way, we have n equations of motion, which is called Euler-Lagrange equations system. Or system of Euler-Lagrange equations. So that's an answer of the first part. So we tried at least to start in abstract form, telling that first of all, we defined what is a system. System is a collection of points. That means that the system is defined by the vector q as a function of time. Then we say that, okay, let's define the motion as a minimum of some functional, which we don't know which one, but let's assume that we can invent one. And then under some mostly natural hypothesis of on what this function must be, what functional must be, we derive the equation of motion. So we have equation of motion. So whenever you give me the function L, Lagrangian function, I have equation of motion, and I solve this equation of motion, which define now the trajectory. So this is just differential equations. We know that you give a differential equation, you give initial conditions. So this is a system of differential equation. And normally, if it's a good system, which means it's satisfied, if it satisfies the uniqueness existence of solutions, then you give initial condition, you find trajectory, so you can predict the motion. So the only missing part is what is L? So what is a Lagrangian function? And where you take it from? So this will continue after the break. So break. So this I write for people in YouTube. Okay, so that's coffee. Okay. So the question, what is L? So now, before asking what is L, we can ask if. So if L is unique, so in the sense that whenever it's kind of the inverse question. So let's assume that you have certain certain law for the evolution, which is given by certain Lagrangian function. If this evolution is described by the unique L, so whether we can construct another Lagrangian which gives exactly the same laws of motion. So the answer is no. And why is because consider we can find the full class of Lagrangians which just give exactly the same dynamics. So take any function which depends on coordinates and time at coordinates, just time coordinates, without, so there's no speeds. Take any function and then consider another Lagrangian function where we take the previous one and add the full derivative of that new function. So what it is? Now remember what is this derivative. So this is a derivative along the trajectory when q is a function of t. So let's just, for an exercise, let's open this expression. So time enters in here and in each component of q. So it will be partial derivative and each component, so we have n components. So it's derivative with respect to I component, and then derivative component I with respect to time, which gives you speed. So let's show that this Lagrangian gives just the same dynamics, the same laws of motion. And we will not work with equation. We will just start with the original Hamilton's principle. So let's compute action. New action. So it's an integral of this L. Let's put this expression inside. So it will be two integrals. First integral of this form and the second integral of the second term. But you can see that the second integral can be this integral of derivatives, right? So it's just difference of the values of f at both sides. And the first term is just the previous action, and this term is just will be f at tq between t0 and t1. So this is equal to S plus f ftq t0 t1. So in Hamilton's principle, S attains a minimum at fixed ends. And you can see that it's exactly the same, so it's exactly equivalent to the condition that S tilde attains the minimum at fixed ends. So you see the value of S is different because of this new term. But minimum is attained is exactly the same point, because whenever you fix endpoints, this is fixed. Right? So whenever S attains minimum, this attains minimum. Whenever this attains minimum, that attains minimum. Right? Because this term is fixed. It's minimum is not the same, but the fact that it attains minimum is equivalent. And since the Hamilton principle is the only thing that we use to derive equations of motion, it means that equations of motion should be equivalent. So all equations of motion are equivalent. So the good exercise for you is just to show by substituting L into Euler-Lagrange equations that the equations do not change. Not just equivalent, you will just obtain exactly the same system. So if you start with the new Lagrangian of this form, you just put it inside, make the derivation, and you will see that you have to see that equations are just the same. So it means that there is a freedom of choosing Lagrangian, and this freedom will be very important. Good. Okay. So after we figured out this equation of that L is not quite unique, but still we need L. We still need Lagrangian function. So where you take the Lagrangian function, and so we derive, I will put in quotes, the Lagrangian from a symmetry. So what is the idea here? And this is a general trend of theoretical physics, is that everything we have in nature somehow can be obtained from symmetry. So we don't need details in order to define how everything moves. We just need the symmetry. And this is already comes in an important way in classical physics, which defines at least the form of equation of motion. And it's become much more deep into the quantum field theory, which derives not only form but equation of not only form of this Lagrangian function, but the function itself. And then it gives continuous, at least expectation are even stronger, like in the string theory, which also gives not only form of equation but even dimension of the space where we live. So somehow, from the idea that from a symmetry we can derive everything. So we don't need to know anything else. In classical mechanics, this also works to a certain extent, certainly much less than in other theories. But we will see that symmetry is extremely important, and it gives you an idea what the Lagrangian should be. And somehow this whole idea of symmetry certainly comes from classical mechanics. So it's where it started. So now I will start first with the symmetry which defines the classical mechanics. So it's a space-time symmetries, which is called Galilean. Galilean group symmetry. So that's the symmetry. So the Gaussian group is a collection, is a set of transformations of space-time, which means the transformation of the coordinates xt, which is a point in, so space is three-dimensional, time is one-dimensional. So we need to find, we now will define all the transformation which constitute this generated Gaussian group. So the first transformation is a shift or translation. Shift, it means that you can change. So instead of new previous coordinates, you consider new coordinates x prime by adding a constant. And also you change time by defining new time plus changing a constant. So for some fixed x0 and t0. So what it means, it means that if you have coordinate system xt, so it's like xt, and then you define new coordinates x prime, t prime, so you should put the new coordinate system at the point x0, t0, and then it gives you a new coordinate system x prime, t prime, right? So you just move the origin from 0 to point x0, t0. So the first transformation is just changing the origin of time and space. And the idea is that there is no distinguished origin of time and distinguished origin of space. You can put it here, there, any other place. It will be just the same. Okay, so this is first transformation. The second transformation is rotation. That's another simple concept. So because rotation in space, in three-dimensional space. So this is simple concept which tells you that the coordinate axis which you define, you can put three axes, you can put it in any direction. Right? So just important that they're orthogonal. So that so it means that you can put, just take another coordinate system just by rotating the first one in three dimensions. So and this is also what changes coordinates. So x. So how you define rotation? You define rotation. Rotation is a linear transformation, so it can be defined through the matrix. So without changing time, right? So what is here? Here, here we represent x as three coordinates. We represent x prime also as three coordinates. And then, no, let's not use G. I will need G. Let's put O. It's O. It's not 0. It's O. And O is a 3 by 3 matrix. So this is, if you take 3 by 3 matrix O, multiply by one vector, and you get another. So this is general linear transformation, but general linear transformation is not always rotation. So in order to understand what is rotation, so what meaning of rotation? Rotation, the property of rotation is that it does not change the size of the vector. So the norm of the vector does not change. So it means that norm of x should be the same as not norm of the x prime. And somehow, if you geometrically think a little bit, you will see that this condition is actually enough to define all rotations. So, of course, rotation satisfies this principle. So rotations are already inside this class. But in fact, this condition is slightly more. So it's all rotation and reflection or parity. It's called parity transformation. So which is just when x equal minus x prime. So when you change all coordinates by minus, and this gives you, well, this is, you should have seen before. If you put everything to the minus, it becomes like this. So it's left, right hand. And important is that whenever you change all coordinates by minus, in 3 dimensions, you cannot put them back by rotation. So that's why it's a different component. So it means, preserving the side of the vector, which is what's in mathematics called isometry, will give you all rotation and together with parity. Okay, so we can now just define how this relation relates with matrix O. So let's just compute the norm squared. The norm squared, remember, it's scalar product of, well, the norm squared, if x is a vertical vector from a linear algebra, you can remember that this is this product, transposed vector, which is rho by the vertical vector. And then now we can substitute this expression. Transposition of the product is transposing every component and putting them in the inverse sequence. And this should be equal to norm of x prime, which is x prime t x prime. And this should be true for any vector. So which means that this is only true when this is an identity matrix. Just 1, 1, 1. So that means that we have this condition orthogonality. So that actually completes the definition of rotation. So rotation is any transformation of coordinates with orthogonal matrix which satisfies this condition. Just take into account that together with rotation we also put parity together, but we actually don't need, we will not use parity anyway, so we just keep it there if you want. It's okay. And then the third condition third element of the group, of the generator of the group, is the Galilean transformation itself. So this is transformation which has such a particular form where you add to x prime ut, you don't change time, and for fixed vector u. So first let us just understand what it is. So it looks like change of the origin, but the origin will move, right? So what we have is that the coordinate system, x1, x2, x3. So we change the coordinate to the point which is ut. So the new origin will move, so the origin, new origin in space moves with a constant speed, u. So that's a transformation. So this transformation, well, was discovered experimentally by Galilei and together with other astronomers. So from astronomy, so they was looking on how the planets are moving and found out that this transformation should be there somehow. Certainly, it's strange, because why at all you should move origin in the coordinate system with constant speed? But in fact, we will see that it's actually a observation. We will see that this is an approximation. So the approximation of a space-time isometry for the special relativity theory at small speeds. So actually, this is just it's peculiar just because it's approximation, and you will have exercise which actually shows that you can derive this symmetry from some symmetry which is much more natural, which really the symmetry which just simply does not change the distance in some more complicated space. So so for now we believe in this symmetry, and this is all. This is all we need. So we can define a Galilean group G is a set of transformation of space-time generated by 1, 3. So you have 3 different transformations: rotation, translation, and Galilean transformation, and you can put them. Just take one, take another, take a third, and then in general, the general transformation will have the form. This will be x0 plus O x prime plus ut, right? So this I put all 3 of them. And then for time, it will be t0 plus t. So that's a general transformation. So which means that the elements of G can be represented as, so every element can be represented by what? So by x0, t0, O, u, where O is the orthogonal matrix, u is a vector, x0 is a vector, t0 is a number. So small observation that we do not consider the time reversal here. We will not need it, but you can include change of time as well. Just in the same way how you we may include or not the reversal of coordinates. We can include or not reversal of time. It will not matter for what we do. So the first thing can be an exercise for you, is show that G is a group. And here I will just recall you what means group. This is concept from algebra. And it means that actually the set has a nice structure. So definition of what means group. The group with respect to composition. So let's first define what is group, and then I will describe what this statement means. So definition of group is that any set, a set G with a binary operation. Binary operation means that given two elements, it gives you another element. So you can think of multiplication, addition, and so on. So such that so it's for any AB. So this is the meaning what means binary operation. So given two elements, it gives you a third element in certain specific form. So it is called a group if it satisfies the following properties or following conditions. So three conditions are necessary. Three conditions, in addition to the fact that you have binary operation, you need three conditions to be satisfied. So first condition is called associativity. And it means that whenever you take operation between the two elements and then the third element, it doesn't matter in which order you do it. So you can recognize that in usual numbers, if you take, or vectors, if you take operation as sum or product, it's all right? So it doesn't matter which sequence you use. B, that the condition of inverse element. So which means that for any element of G, there exists element A minus 1, so inverse element, such that A times A minus 1 is the same as A minus 1 times A. No, sorry, inverse is too early. Neutral element. Or identity. Element. So there exists element E, which we call E. of the group such that E times A equal A times E equal E for any element. So identity element means that when you add or multiply by this element, you don't change. So clearly, for the if star is addition, E will be 0, and if a star is multiplication, E will be 1. Okay. And third is inverse. So now it's for any element of the group, you can define the element A which is called A minus 1, also from a group, such that A times A minus 1 equal A minus 1 times A equal E. Again, if star is an addition, then A minus 1 is minus A, right? So if you take if operation is adding two numbers, the inverse number is just you change sign. And if if star is multiplication, it's then A minus 1 is 1 over divided by A. So that's naturally, it's a natural generalization of the properties of real numbers. So what I'm telling here is that G, this G that we have Galilean group, is a group in that sense. So what is operation? Operation means a composition. So you take any element of group G, it changes coordinates. So now you can take another element of group G and change coordinate again. So the star means that you change coordinate first time with respect to the first element A, and then make another change of coordinate again with respect to element B. Right, so you first you change origin, you rotate it and made the transformation to Galilean frame. So it's A. And then you get B with another change of origin, another rotation, another U, and applied it again. And so what first property tells is that when you do one transformation and another transformation, it still has the same form, but with a new x0, new 0, new U. So it means that it means that if A is given by this transformation, B gives you another transformation, it's prime. Let's put tilde. Then it also has the form, but with some different components. So this is the first thing which actually have to be shown because it's not obvious, not directly. And then you have to show that it's associative. So if you make, it doesn't matter if you first combine the first two transformations or the last two. Then there is quite obvious part B. The identity element is when you take everything, when you take x0 to be 0, u to be 0, t0 to be 0, and O to be identity. So you then change coordinates. Of course, if it's natural identity element. And the inverse element also exists because if you made this transformation forward, you can also make it backward. So these three conditions, but it's useful to write them explicitly, right? So just writing identity element is that A is 0, 0, identity matrix 0. Inverse element is a bit less trivial. Let's make it. So the inverse element. So let's write it x0, tilde, t0, tilde, o, tilde, u, tilde. So a minus 1 star a is what? So you have to apply first this transformation and then apply the transformation again. So we have the A defines x as t0, no, x0 plus O x prime plus ut and ut prime, no? Let's write primes here. And then t equal t0 plus t prime. And then a minus 1 is the next layer. Right? So we made the first transformation and then we made the second transformation. And what we should see is that the x double prime and t double prime are just the same coordinate as the previous ones. So just combine them. What we do is we substitute this into the upper one. So x equal, I'll write it separately. Equal 0 plus O. Here there is x prime, which we put the lower relation. And t prime, no, sorry. How we do it? Here there is one more prime. Okay, good. Okay, let's do it step by step. So we had x equal x0 plus O x plus prime t prime and t equal t prime. So now we substitute prime, the primed variables from the second line. And here as well. This is first, and here we'll have okay. And what we need is that, so if we take t0 tilde equal t0, then here you get identity, right? So if you choose this connection, you have identity, which means that in this expression, what will be left is x0 plus O x0 tilde. Then you get, no, I forgot. No, it was u, no? It was u multiplied by u. Also, let's put this term. No, this term I will not put. So I combine these terms plus O tilde x double prime plus O u tilde plus this T0 u double prime plus T0 tilde. Let's put it here. Like this. So now we can find, so what is this? So this is first. We know that T0 tilde is T0. Minus. Don't follow. Minus T0 u 0. No good. No, there is something. This is not tilde. This is u. So it means that this is tilde, this is not, this is, so T0 normal u, and this is O, T0 normal u, like this. Okay, so we found that U tilde is inverse matrix by T0 U. So the second relation. And then this should be identity. Well, this is this should be identity, which means that it's just inverse matrix. And then this one. So x0 plus O, x0 tilde plus T0 u, and we want it to be 0, which gives you, so remember that this is minus T0, so this just make your computation. So we need to derive x0 will be O minus 1 by all other terms, so minus x0 plus T0 u. Okay, so I'll just summarize. That the inverse element, which is composed by this transformation is just what? X0 tilde is this. T0 tilde is minus T0. O tilde is O minus 1. And U tilde is here. T. Oh, there is no T0. So we really found the inverse element. And it's, you see, it's not so simple, it looks like. And this is it's not simple because of the representation. With this representation, the inverse element is unique, and it's given by this free coordinate. So given any transformation, you get an inverse element. And so you can try to fulfill the rest, because so what is missing in order to see that it's a group is to show that whenever you have two transformations of this kind sequentially, you still have the same form, which is kind of direct calculation. And also, it's a direct calculation just to show that whatever sequence you put, it will give the same result. So it doesn't matter how you do. So it gives you, just proves that it's a group, and having a group is a very strong property because we have all these algebraic relations that we know for the group theory. So it's very useful. So so why we do this all? So I will just announce, and we will continue tomorrow. So what is the idea? Is that the idea is that so we assume that there exists a coordinate system which is called inertial reference frame. Such that laws of motion are invariant with respect to the Galilean group. Period. So we say that we can choose coordinates in our space-time, such that in that coordinates the laws of motion will be the same whatever change of coordinates you do under this group action. So it means that whatever origin we put in the system, whatever rotation we apply, whatever Galilean transformation we apply, it will not change laws of motion. It will not change the way how the system evolves. It will not change the equations of motion. So all equations of motion are invariant, will not change under all this transformation. And this is purely symmetry statement. So we don't tell what the system is. We just tell that it's the system in certainly properly chosen coordinate system. It will not change under elements of the group. So what we will see is that tomorrow is that we will see that first of all it defines the Lagrangian of a single particle. So now, using just symmetry consideration, you can find what is L for a single particle, including it will define concept of mass. So mass will come out from symmetry. And also it will define, to a certain extent, the form of a general system. So the Lagrangian function will not be given explicitly already for many particles, but we will have at least a certain structure, very restrictive structure of the Lagrangian function for arbitrary number of particles, including with all usual conservation laws that we have: conservation of energy, conservation of mass, conservation of energy, conservation of momentum, angular momentum. It all will follow from that property of invariance with respect to the group. That's why we go this complicated way. You know, it looks abstract and maybe much more complicated than just using concept of starting with Newton's law, but it gives you much more vision of why it happened, why we have such a rich structure of the dynamics, and what is a possible initial origin of this structure. So we will see that it's a Galilean, for classical mechanics, it's a Galilean group. Okay, so tomorrow, same time, and I think tomorrow I'll give you first, I'm not sure, but probably tomorrow I give, first exercise. It will be either tomorrow or Monday. So we will have exercises on a regular basis. I will try to give it every week. So you have exercises, you se inscreve ou manda. Okay. I guess that some considerable part of people look it in the YouTube, which is today's reality, but who looks at YouTube and who wants to have a mark should send probably to me, and then we'll see what we do. As for the evaluation, we will have exam at the end, as I said, after the carnival we'll have exam, and it will be written exam because I'm supposed to travel, so there will be monitor, and he will also help with exercises. So this, but we will resolve it as soon as we get exercises. Okay, so see you. Até amanhã.